One of them, the first one we're going to talk about, is called a standing wave. We're specifically going to look first at the standing wave on a string. Yes?
Is wind considered a wave?
Wind would not be considered a wave. Not that I know of.
Well, I just wondered because of that bridge that was going up and down.
It can cause waves. So yes, the wind caused the wave to be created on the Tacoma Narrows Bridge. Yes. But the wind itself wasn't the wave. It's how the wind, as it passed over the bridge, how the forces it exerted, it kind of pulled on the edge of the bridge. And the rate at which it pulled on the edge of the bridge caused the bridge to start oscillating.
So, and if would it keep on pulling approximately the same speed as the wave was going to make the wave go high, make it vibrate
Yes.
more and more?
Yep. Exactly, resonance was the example there. The concept actually of the standing wave on a string is considered a resonance situation as well, because you're causing the medium to oscillate at a natural frequency, at a frequency in which it makes the amplitude get big. Okay, can I borrow you again? So here's our string. When we have a wave on a string, actually when you have any wave, quite honestly, if the wave hits a boundary of any sort, it will at least be partially reflected. So here, this wave is partially reflected. It goes down, hits his hand, comes back, hits my hand, goes back. Okay. Now, it certainly dies down with time. One interesting thing that happens is when we're holding tight, holding on to the ends of the string, the wave, when it reflects, it actually inverts. So here, I'm pulling down, but when it comes back, it's oriented up. Okay. So on any rigid boundary, anything that's holding it, you will always have an inversion when it reflects. It turns out, if I don't have a way to make this not rigid boundary, if you have a boundary that's not rigid, then it will not reflect as it it will reflect, but it will not invert on reflection. And that will come into play in a little bit. So it turns out, if I continue making waves, so I continually disturb this medium, the wave I produce and the reflection coming back actually interfere with each other. They end up superimposed. If I get just the right frequency, which would be considered a resonant frequency, if I get just the right frequency, we end up with nice, perfect constructive interference in the middle there, and destructive interference at these ends, because there's very little motion of the ends, but there's big motion in the center. This is called the standing wave. So it looks like we can play jump rope. Okay. This isn't the only pattern we can get, though. This is the simplest pattern you can get on a string. If I shake it at just the right frequency, I can get two. The loops, those are positions of constructive interference. Those are considered antinodes, is what we call them. Notice not only the ends, but now we have the middle point that isn't moving very much. Those are points of destructive interference. Those are considered nodes. That's what they're called. I'll try, but I'm not sure if I can get it. There we go. If I get it at the right speed, I can get 3 of the antinodes. Kind of hard to do. So there's certain frequencies that allow for standing waves to occur. So that simplest pattern we saw is when we ended up with one big loop. The string just vibrated up and down in that middle part. So this loopy part here is called an antinode. The ends are called nodes. This simplest pattern is called the fundamental. If you play a stringed instrument, this is primarily the frequency you're getting. So whether you're plucking the string or you're drawing a bow across it, whatever type of string instrument it happens to be, this is the primary type of pattern you're getting on the string. there is a very specific frequency that allows for this to happen. The next pattern that we got, if we were shaking it a little bit faster, we didn't change the length of the string, but the pattern changed. The pattern changed so that we saw two antinodes. Sorry, my pictures are a little schemoless. This would be called the second harmonic. For those of you who are musically inclined, this would be an octave higher than this one. Okay? If you're not musically inclined, then don't worry about it. The next pattern, when I shook it even faster, we ended up with three antinodes. This would be considered the third harmonic, which in turn would be another octave higher. Okay. Turns out, when we have standing waves, when we have a wave interfering with its own reflection, the wave equation, if you add them together and you work through your trig identities, the wave equation ends up looking like this. It ends up being a sine of the kx term times the cosine of the omega t term. Little a, your book uses to represent the amplitude of the individual waves. This term right here, the 2a sine of kx, that determines the overall displacement at any point in the medium. This determines how much, in this case, the string has been displaced from its equilibrium position depending upon where on the string we're looking at. Has the x in it. X, remember, is where in the medium we're looking at. Okay? We can use this to find a nifty little relationship. It turns out our string, the section we were vibrating, that we're shaking, had a fixed length. We weren't changing the length of the string at all. So it had a fixed length. So if we consider a coordinate system, y-axis there, the x-axis here, this would be x equals 0. This end would be x equals L. Because the string is L long. L being however long the string happens to be. It turns out these are both nodes, so the displacement of the medium here is 0. It hasn't been displaced from equilibrium. It's a stationary point. Any node has a displacement of 0. It stays in place. That's a point of destructive interference. Well, looking at this, basically this term here needs to go to 0 in order to satisfy the nodes. So at x equals 0, if we put 0 in for x, we need to get 0. If we put L in for x, we need to get 0 as well. A is not 0. The individual waves have an amplitude that is not 0. So the only part of the function that can go to 0 is the sine term. So the sine term has to go to 0 when x is 0 and when x is equal to L. That has to go to 0. You okay with that?
I meant at the nodes.
That's the node specifically, yes.
Okay.
Exactly right. Okay, well, sine of 0, we know sine of 0 is 0, so we're good for this one. What about that one? We're going to put in L. For x. Now, L is not 0. There is a length. The string has a length. So L is not 0. So the sine of what angle other than 0 will give us 0? 180 will. 360 will. So forth. Now remember here that K has units of radians per meter. And so our calculator would have to be in radian mode if we're doing this. So our angle needs to be in radians. So pi would work. 2 pi would work. 3 pi would work. 4 pi, so forth. So let me modify this. Any multiple, any whole number multiple of pi is going to give us 0 when we take the sine of it. You right with that? So m is just a multiple. Meaning it's 1, 2, 3, 4, so forth. So it's just a whole number. We know the sine of pi is 0, the sine of 2 pi is 0, the sine of 3 pi is 0, and so forth and so forth. Okay, so this condition right here will give us a node at the end of our string. K. Remember K is equal to 2 pi over lambda? The pi's cancel. We solve for lambda. This equation tells us the possible wavelengths that can exist on our string and give us a standing wave. There's only certain wavelengths that will work. Only certain wavelengths will give us the nice standing wave patterns. If m is 1, we have the fundamental. Okay? So the smallest multiplier here gives us the simplest pattern. So if m is 1, then we have the fundamental. That means the wavelength of this particular standing wave is exactly twice the length of the string. Which should make sense. If I trace out this wave, so if I start here, trace out the wave and go to there, how much of a wave have I traced out? So L was half of a wavelength, which means wavelength is 2L. It's another way to look at it. Okay. The second harmonic, so the second pattern corresponds to the second multiplier. So n equals 2 is the second harmonic. If m is 2, then the wavelength, putting in 2 there, we get 2L over 2, which is L. Which, if you want to look at the pattern, if I trace out from one node to the end node, that's one full wave. So the length of the string has one full wave on it. Okay. This one, the next harmonic, is 3. So it turns out the m values relate to the harmonic numbers. The fundamental is sometimes called the first harmonic. So the m numbers correspond to the harmonic value. The wavelength, if we put 3 into our equation there, 2L over 3. Our wavelength will be 2L over 3. Which, if you want to follow the pattern, there's one wavelength and a half. So the length of the string has 1.5 wavelengths on it. So wavelength has to be 2L over 3. Wow, 15 minutes goes fast. We'll continue with this tomorrow. We're going to use our equations that we had from last chapter. Remember, what determines the speed of the wave on these strings? The tension and the thickness. So we're going to use that equation, but we're also going to use the wave equation that relates the speed to the wavelength and the frequency. So if we haven't changed anything about the string, then the speed's going to be the same. Knowing the wavelength is related to the length of the string, we can easily find the frequency. Okay? So we started talking about standing waves on a string at the end of class yesterday. Just as a quick little review, a standing wave on a string is when you get the antinode and the nodes. The simplest pattern here, looks like you're jumping rope. The simplest pattern is called the fundamental. The frequency required to produce this pattern is called the fundamental frequency. Okay, there's a very specific frequency required to make this occur. The fundamental is also sometimes called the first harmonic. So if you see that, it means the same thing as the fundamental. So we mentioned, reminded you yesterday, the speed of a wave on a string depends upon the force of tension, so how tight the spring is, and then the thickness of the string, how the linear mass density. So the wavelength here, we had our equation for wavelength for our standing wave on a string. The wavelength is equal to 2L over m, where m is just a multiplier. It's a whole number, 1, 2, 3, 4, so forth. M equals 1 is our fundamental, our simplest pattern. That means our wavelength, if m is 1, our wavelength is 2L. So the frequency will be the speed over the wavelength, which is 2L. So the fundamental frequency is v over 2L. Another way to see that the wavelength is equal to 2L is to trace the pattern. If you start on the left and go towards the right, how much of a wavelength have we traced out? Half of one. So L, the length of the string, is showing 1/2 of a wavelength. Well, if we solve that for wavelength, we get wavelength as 2L. So there's two ways to figure out that wavelength. You can use the equation, or you can just trace it out and figure it out that way. The next pattern we can get, which requires a specific frequency, basically the next pattern just adds an antinode into the picture. So now we have two antinodes rather than one. This is called the second harmonic. M is equal to 2. So the wavelength will simply be 2L over 2, so L. So F2 is V over L. Notice the wavelength going from the fundamental to the second harmonic, the wavelength was cut in half. Which means the frequency, how much did the frequency change by? It doubled, exactly right. As the wavelength cuts in half, the frequency will double, so that when you multiply wavelength by frequency, you get the same speed. Because we haven't changed the tension in our string. The next pattern ends in another antinode. This would be the third harmonic. So m equals 3, which means wavelength is 2L over 3. So the wavelength compared to the fundamental is 1/3 of the fundamental. So the frequency should triple. The frequency will be the speed over the wavelength, which is 2L over 3. If you compare the fundamental frequency by this F3 frequency, this is 3 times bigger. So basically, the main equations we get, we have our wavelength is 2L over m. We can write our frequency in terms of some m frequency. It'll be mv over 2L. M being the multiple, it's the harmonic number. And we can also write as m times the fundamental frequency. The second harmonic is twice the fundamental frequency. The third harmonic is 3 times the fundamental frequency. The fifth harmonic would be 5 times the fundamental frequency, so forth. That means as you go 1 octave along, the difference between the frequencies is always the fundamental.